Alrighty. Well, welcome for folks who could make it today. And we are going to be hearing from our guest speaker, Leonardo de Silvestro, and he's going to be telling us about Loom, which is a Python library for a simplified setup of quantum error correction codes. We might get to see a little bit of the Entwine GUI that they've built over in Entropical Labs. And so without further ado, I will go ahead and hand it over to Leonardo.
Thank you. Very happy to be here. So let's start first things first. Let me try to share my screen and start our presentation. It's going to be a bit interactive, so um, I will be showing a few. Tab. There we go. I hope you can see full screen. I think so, and I can see you. Perfect. Yep.
Yes.
Okay, so thank you for being here. It's going to be a bit of a back and forth. There's going to be some live demoing, and the goal of today is really just that of introducing Loom Design and well, letting you know people about it. Um, I will say this up front. First, I really hope Loom Design will help people onboarding on QEC, quantum error correction, and I think it can make, especially with the graphical interface I will be showing you, can make it a very interesting user experience, almost a little bit like a game. So first of all, what's Loom Design? Loom Design is really the union, if you want, of two separate tools, Loom and Entwine, and just a bit of a mouthful. It's a free and open source toolkit to learn, design, explore, and validate quantum error correction experiments. And we'll sort of go through it and see what each part means throughout the presentation. If English is like, if you're not a native English speaker, like myself, I wasn't quite sure what a loom was at the very beginning, and that's a picture of it. Indeed, is the tool you can use to sort of weave together threads, and we felt that that's a pretty nice metaphor for quantum error correction, for sure, and not the only one. I think is a metaphor you can see you'll find quite often, the sort of all weaving vocabulary. And very quickly, Entropical Labs is a startup based in Singapore. I'm not currently in Singapore, I'm in Italy, but I think it's always nice to see some of the faces and people that actually build the software. So we're around 20 people, and you may have crossed paths with some of us throughout your careers. Okay, Loom is an open source Python library, as I said, and we really use it to build complex quantum error correction workflows. I hope you can see my mouse, but it's not super fundamental. You can find it on GitHub at entropicalabs-loom, EL-loom, and it's released under the Apache 2.0. The reason why we chose this license is that it seems to be a standard in the industry, and most people feel comfortable using and building their own tools based on this type of open source software. So that's why we went for it. And to the right, you can see a quick example of Loom source code. We'll go through more details later, so no need to have too much to put too much attention to it. But the rough idea I want to convey here is that you will have some a builder interface. So you'll be able to do rotated surface code dot create, and with a bunch of parameters, create a logical qubit. So that alpha will be a logical qubit, and again, blocks, operations, as always, of stacking these things together. And eventually you create this object called ECA. I'll tell you in a moment what that is, and you interpret it. But the idea is we try to make the whole process simple. On the other side, I said there is Loom and Entwine. Entwine is a graphical interface. It works on your browser, so you can just go to entwine.entropicalabs.io. You need to register with an email address, and then you're good to go. So you see at the bottom, it's the creation of a rotated surface code. And the color code identifies as X's and Z stabilizers. And it's a quick way of putting these logical qubits on some lattice and then moving stuff around. The idea is that especially rotated surface codes and lattice surgeries later on are highly geometrical, and visualizing things may be quite like there is a sweet spot maybe when you're dealing with up to 10, 20, maybe even 30 logical qubits, and it's nice just to put them on a screen. Now, I was at a conference, the Munich Quantum Software Forum, a couple of weeks ago, almost a month now. That's a slide from IQM. Over there, any quantum hardware company has a similar roadmap. So I just took this as an example. The IBM one is a bit shift to the left, so they claim everything is coming a bit earlier. Some like IQM push it a bit further down the line. But what I want to focus is that there's going to be an interesting time in the next year where we're going to have thousands of physical qubits, and we'll start having tens of logical qubits. And the question is always a bit the same. What are we going to do with these resources? And an assumption which wants to be an answer a little bit to this question is that the world will be very, very hungry for quantum error correction. Some companies, some hardware companies will just do it all themselves. So I'm thinking maybe about PsiQuantum, maybe IBM as well. Their plans, as they've spoken, is we'll just give you logical qubits, forget about the physical ones. That's fine. There will be other companies. I'm not saying IQM will be one of them in this case, but there will be other companies out there that will give you more control. So you will be able to define your own logical qubits. And I think there's going to be a lot of value in trying to test quantum error correction routines, tweaking these quantum error correction algorithms. So really the scaffolding on top of which real applications will be built later on. So the plan for today is a little bit about Loom, its philosophy, what's inside it, then moving to Entwine, the QEC graphical user interface, then the memory experiment, so the simplest kind of experiment you can do using, so the first meaningful thing you will do in quantum error correction, and then I'll talk about the different backends you can target with Loom, talk a bit about logical operations, some custom codes, and give some perspective at the end. Should take about half an hour, 40 minutes, depending on how fast I go. So the philosophy of Loom. What you see here is the code structure in the repository. The only thing I want you to focus here is, if you go down the hierarchy, you'll see Loom and you'll see some folders. Now, the first one is this ECA. And the idea is that the ECA is the single source of truth for the whole quantum error correction code. Now, Eka comes from Sanskrit. It means one, first. And the idea is to have a single data structure that contains everything you need to know about the algorithm that you're set to explore. The assumption we're making here is that we want to put the data structure first rather than later. And I'll motivate this in a moment. So inside this, you will find definitions for all the static things and a little bit about the dynamic things as well that you will need for quantum error corrections. The ECA then is interpreted. The interpreting the ECA step, of course, these are just arbitrary name we picked. Maybe eventually we'll figure that there's better ways to call these things. But interpreting the ECA means that you generate a circuit. So the idea again is you don't start from the circuit. You start from a data structure, the ECA, and the circuit is obtained as a byproduct. And this is a circuit in an abstract sense, so it's not quite a quantum circuit as you're used to them. But the idea is that all relationship between different parts of your quantum error correction code are together. So there is no place where you can execute this just yet. It's just a way of representing and working out relationship between different parts of the quantum error correction codes. And once your circuit has been interpreted, then you can translate it into some executable source code. Steam, CUDA, PennyLane. I'll go through them after. I know everything sounds a bit abstract at the moment, but it will become more clear in the next slides. So the idea is that with Loom, you can build a static scaffolding for your quantum error correction code. And then you obtain something that you can execute only later on. The idea of having some scaffolding for QEC, I think, is something quite neat in general. It's the kind of idea that in quantum error correction, you have a lot of static parts that need to be defined. And then at some point at runtime, you kind of need to put all of this back together. Simplest example will be syndrome extraction circuits. That's something you need to do over and over and over and over again. So just giving you the full circuit for that may be suboptimal. I'll go back to this idea. So at the very least, I hope you'll be more familiar with this terminology by the end of the presentation. Steam. If you're not familiar, Steam is a stabilizer simulator developed by Craig Bidney. And the idea is that Steam, as you can see here at the bottom, um, uh, an API to build circuits, which is very similar to what you would expect from a quantum circuit, right? It's what you use with Qiskit, penny-lane, circ, anything else. Like you append an Adamar, the C knot between two wires or qubits, and so on and so forth. The problem with this is that there is no problem, really. Like Steam is a simulator. So it does that job really well, and it gives a pretty relaxed interface for building the quantum circuit. But what we think is that circuits are not the best primitives when it comes to quantum error correction codes. Now, this is a very fascinating topic. I'm sure this has been explored in other times at UF. Circuits may not be the best way to think even sometimes about quantum error correction. Indeed, measurement-based quantum computation or other models of quantum computations don't really work with circuits either. So maybe sometimes in the future, we will have different kind of abstractions for this. And the idea is that for quantum error correction, it's much simpler sometimes to just reason about other concepts and just obtain circuits as a byproduct just at the end. So again, the idea is that from Loom import ECA, and then my ECA will be the union of these three data structures: a lattice, a space where my physical qubits live, blocks, so my logical qubits, a definition, something tells me what's a logical qubit, and then operations. So a list of operations that tells me what's going to happen in this logical qubit. Yes, that's exactly what I said. Okay, let's look at the first example I gave you. That's a memory experiment, really. So what we do is that we have a lattice. Let's put that on the background for a moment, some cycles, and you define a logical qubit with a bunch of parameters. So that's a rotated surface code. We have a single logical qubit in this example, and then have three operations. The operation are reset all data qubits, measure block syndrome, measure the logical Z stabilizers. If you note, this measure block syndrome takes as input the number of cycles, so this is happening 3 times, really. The reason why usually a cycle happens more than once is that you want to generate a logical qubit and then start a clock and wait some time and see that you still have that state at the end. And finally, we interpret it with the ECA. Now, the idea of Loom is that you hide all the complexity of this function, the logical qubit.create, elsewhere. So what you see here, it's really the way that I'm constructing the block in the case of a repetition code. I use the repetition code just because it's less to display, but it can be any code. So it will have a label, it will have some names. So stabilizer will be Z, the ZZ and ZZ, different qubits, and Scylla and the logicals. So you just have a recipe on how to build this in general. Once you've done it, it's fine. You have your block, and then you can reuse it in this type of problems. So yes, and we will see in more details how you do this for other codes later. Now, for the operations, there are 2 types of operations. There is some templates that are well defined for most codes out there. So measure syndrome, reset data and syndrome qubits, the logical operations, both measure and application, the state injection, conditional logic. These are all available for all codes. So once you define your logical qubit, your blocks, then you have implicitly, in an implicit way, you have defined all this already. So you have ways to define these operations out of the box immediately. For the rotated surface code, there is a bit more. If you're not familiar with the rotated surface code, we'll see a few examples of this later on. But grow, shrink, merge, and split are basically your lattice surgery operations, what you may be familiar with. And then Hadamard, C0, move logical qubits, and so on are more complex operations that you build on top of this. And we will also have T-gates by the end of the year. So if you're familiar with quantum error correction and stabilizers in general, you know that Clifford stuff, it's easy. You can simulate it efficiently for hundreds of thousands of qubits, no problem. But as soon as you throw in a magic state, a T gate, stuff becomes difficult, and that's what we have here. Now, Loom comes pre-built with these 5 codes examples. The most important one will be the rotated surface code. Then you have the repetition code, which is great for testing small things. And then you have 3 small codes, the 5 qubit perfect code, Shor's codes, Steam codes. These are smaller codes, but they can be pretty nice for real world applications. So if you wanted to try to run something on a quantum computer, these are pretty small. Rotated surface codes require quite a fair amount of qubits. The order around 20 per logical. And not all operations, so if I go back and I see all the operations that I have here, not all these operations are well defined for all codes, of course. So these are dependent on which code you have. Now, let's move quickly to Entwine. When you log in into Entwine, that's what it looks like. Now, one thing that I should stress is that Entwine is free to use, but the code itself is not open source. Now, when you see the green stuff appearing next to a block in Entwine, what's happening is that Entwine, the front end, talks to an instance of Loom and verifies that what you've drawn is indeed a valid surface code. So the scientific backend behind Entwine is open source. It's Loom. What we have not open source is the JavaScript front end. I just want to make that clear. Bunch of reasons for that. The main one is that we wouldn't be able to support a stream of commenting going on for that, and at the moment it's just much easier to handle it as a closed source project for that part, but nonetheless free to use. As I said, you can create stabilizers X and Z just by dragging your mouse around vertices, and you can create logical qubits pretty easily. If you're correct in the logical qubit, it goes green.
Wait, Leonardo, I have a quick question.
Yes, go ahead.
I think like 2 or 3 slides ago, you showed a screenshot of like what I thought was maybe documentation for the different codes that had been pre-built into Loom.
Yes.
But I'm having trouble finding that if there's documentation.
There is documentation. I have a slide at the end of the presentation, but I give it to you right away. So actually,
I'm on loomdocs.entropicalabs.com.
Loom-docs. If you go at the very end, there is documentation, source code, and API reference. If you click on the API reference, then you get the place where I got that screenshot from.
Okay.
So this Sweet. Is the loom-api-docs.entropicalabs.com, and on Code Factories you'll find them.
Perfect. Thank you.
No worries. Okay, you can also copy paste. So this is some helper utilities if you want, and you want to reproduce stuff around. And let's go and try it out. So you should be able to see my screen here. Again, you can just draw things pretty easily. If you overlay stuff, you will get things like this. The color means that you have some, it will tell you the number of X or Z's or Y operators left there. And if I hit Command or Control Z, I undo everything. Now, there is also like a builder for this one, so I can just quickly build a surface like this. So all you need to do is just select it. Next, what I want to do is if I press the letter S, I enter the lattice surgery mode. So for the lattice surgery mode, it allows me to stack lattice surgery operations and see them live here to the right. So if you look at this code, it's very similar to what we saw before. So all I want to do for memory experiment is just all the letter Z and measure it. So it's disappeared because measurements are destructive, and I basically distract my logical qubit by measuring. So if I press Q and E, we'll see a bigger example later. I move, actually I can show you now. So another operation I could do is I could grow my patch, another frame, I could shrink it, another frame, and I could measure it. So in this case, if I press Q, you will see that stuff is happening. And if I press E on my keyboard, you'll see it's going for it. It's a little bit like playing video games. And again, on the right, all of this is codified. So, you know, if you see the shrink operation or the grow operation will have a bunch of parameters, and you can either do things visually or you can just programmatically build all of this. Now, what I can also show you is I have a small collab example. Actually, let me go back to Entwine first. What you can do is you can also copy the code from here. So if you see this blue thing here, it's a way of copying the code. If I go to output, I can also find it here, and here is automatically giving me the steam circuit or the chasm. So you can see these are pretty large circuits already. So if I go to my to my memory experiment, and I share this tab, so I pip install Loom, and then I just do a few imports, and this is my the code I've generated from Entwine a few days ago. Everything is here from my rotated surface code example, the blocks, the operations, and the ECA at the end. Now, if I look at the ECA, that's what it looks like. So it's not supposed to be human friendly. So you're not supposed to read it. I mean, if you work with it, you know where to look for some stuff, but it's basically just a printout of what's in there. So this is a representation of the data structure that contains everything you need to know to run this experiment. I can also interpret the ECA. When I interpret it, things start taking space. So this resembles a bit more like a circuit. There is some time steps and there is some operations happening. The way you see here is basically sort of telling you all the what's happening each timestamp and how you're doing the syndrome extraction circuit. Remember, each patch you see needs to have its own syndrome extraction circuit, and you need to take the measurements up. So here you don't see the labels; they're there, of course. It's just a way that Python is printing all of this. But if I go down, I start seeing, okay, now some of these things will have IDs, and you have some measurement IDs associated with it. And then if I go down again, here it gets a little bit messy to see, but I start seeing things like syndrome measurements, some classical registers, some corrections, the space coordinate for it, the time coordinate. So everything starts coming together. The idea is that you're not supposed to look at this, but you're supposed to be able to access it if you need. And so it starts being a bit complicated, but again, it's not meant to be human friendly. So what we do then is we use Steam to simulate. Steam, I repeat, it's a great resource for any stabilizer simulation. I highly suggest you check it out. You can do a lot of really cool stuff with it. So what we have in Loom is a bunch of converters. So we can convert the ECA into some target language. And then we run the simulation. And after all of this, so all we're doing here is that we just do our Tableau simulation. That's how Steam works. And then all we're doing here is we're collecting the last element of the Steam simulation, because Steam will return you all the measurement outcomes for all the syndromes you have. If you look back here, there's a lot of measurements happening. So you need to select, in this case, the last one, sometimes may not be the last one, to see. So what we've done here is that we basically have simulated the whole thing, and we checked that our final measurement was 0. We started in the 0 logical state for the block, and we obtained the 0 logical state at the end. All good, as expected. Now, very quickly, we have a bunch of backends you can connect to. On this diagonal, you see Steam and Entropica Labs Clipper Simulator. These are two pure stabilizer simulators. We developed our own because there were features of Steam that were missing, and especially for debugging some stuff, it was very useful to have one. But in terms of speed and for many practical purposes, Steam is also what we always use internally. We then also have the NVIDIA and PennyLane directive. A lot of work on QIR over there. So it offers like a one-stop solution, if you want, really, to put together classical and quantum computation. This is particularly important if you think about decoders. We also support QASM 3.0, so anything that goes done with Qiskit. And we have the Continuum integration also through GAPI that integration is ready. We're just still in the process of porting it over to the open source repository. So very quickly, bird's view on all of this. All of these backends support Clifford simulations. Some of them support classical control flow. Classical control flow will be if statements. So the basic ones will be if my measurement outcome for this physical qubit is 0, do something or do something else otherwise. Non-Clifford simulations, these are only supported by the lower three. So NVIDIA, PennyLane, Catalyst through QRAC. It's also a project you guys should be familiar with, and QASM. And finally, the hybrid compilation part. So here is not just classical control flow, but is if you want to do more. So if I want to, the example I usually make is if you want to compute a square root based on some measurement outcomes, well, good luck writing that in terms of if-else statements and for loops. I'm sure you can, but it seems a little bit like reinventing the wheel. So there are some ways that you can do these things with NVIDIA, Catalyst, and Kinski. Now, the logical operations. So with Entwine, I showed you some before. We'll go through all of them now. You can do lattice surgery operations. You just need to press the letter S. And once you do, you can start modifying your patches. So the basic operation you have is grow and shrink. So you just take a logical qubit and you make it bigger or smaller. More interesting are the merge and split operations. So merge is I take two blocks, two logical qubits, and I merge them, I fuse them into one. Split is the opposite. I have a single long qubit and I split it somewhere. Now, these operations are quite interesting, and they're also a good way of sort of stressing again why you don't maybe want circuits. So each square here, when I write a syndrome instruction circuit for it, there is an ancilla qubit in between. So there are 4 C knots, physical C knots happening between them. Usually there is a bunch of Adamart, and then there is a measurement outcome. Each timestamp in my QEC protocol requires to run the full extraction syndrome for all these patches at least once. And as I do this operation to make sure that I keep catching errors, I need to do it for multiple cycles. So effectively, this underlying little syndrome extraction gadget happens all over. And for each orange square, it's the same circuit that you need to just rewrite all the time. So the idea of having to write it so many times and consistently make sure it happens, for sure, you could just do with some for loops, seems a bit unnatural. And the second thing is that in a quantum mechanical sense, the idea, especially for like a split, of taking a single qubit and generating 2 qubits out of it doesn't make so much sense. I can't measure a single qubit and get 2 qubits out of it. It's a bit of a counterintuitive operation. But what's really happening here is that you are working not with physical qubits, but encoded qubits. So the fact that you have this long horizontal qubit means that in reality, you have much more space that you can carve out for encoding more information. Now, both of these are entangling operations, and we'll see they're quite useful. So what we want to do now is a C knot. We're going to do a C knot between 2 qubits, and that's the auxiliary C knot. So the first step is putting 2 qubits in this particular way. So you want them to be diagonally aligned. The next operation will be some lattice surgery operations on them to perform the C knot. So what you want to do is turn the first one into plus. You're going to grow to the right. You're going to split. That creates entanglement between these two patches. And then by merging the auxiliary patch with the bottom one, you sort of move these correlations from the first patch to the second one. So again, grow, split, merge vertically, and then shrink it back down. Doing this is a lot of physical circuits, and it's much easier to do this graphically in general. So what you end up doing here is implementing a C knot between these 2 qubits, just that you have implemented at the logical level. some small caveats, but you can check the docs if you're curious to know more. We also have a 3D visualization, if you're familiar with TQEC. So you can't program it through Loom, but you can visualize it. So once you've drawn your circuits in Entwine, you can check them out using the 3D visualization part. If you're familiar with TQEC, the tool by Austin Fowler and the community, we are working closely with them to make sure that Loom can integrate nicely with what they have. We don't repeat too much work between the two groups, and broadly speaking, we just make quantum error correction better. Okay, so before we go to this one, I want to show you a very quick demo using Entwine. I'm back to the same before, I'm just resetting. So the idea is that I can also do a logical GAZ, and preparing a GAZ state is an interesting example because it shows that you may want to do things a bit differently when you deal with lattice surgeries. So a GAZ, if you forget, is the 0, 0, 0 plus 1, 1, 1 state. And we're going to do it in the following way in a lattice surgery context. So first of all, I generate a patch. I need to count. Perfect. I made it length 11. That's what I need. So I generate my patch like this, and I start. I go to lattice surgery operations. And the important thing to remember is when I split, so, here I have a lot of potential information because this is an horizontal patch and it's a pretty long one. So what you may want to do is you may want to think, can I use some lattice surgery primitive to induce the final state? And the answer is yes, you can. It is very similar to measurement-based quantum computation. So if you're not familiar with any of these concepts, it all feels a little bit like magic. But what I claim is that if you measure these 3 qubits and you update your stabilizers correctly so that you're in this configuration, and you measure also these 3 qubits, so you've performed 2 splits. At the end of this circuit, you end up with 3 logical qubits, and their state is exactly 0, 0, 0 plus 1, 1, 1. So let me repeat. I start with a single qubit in the plus state of distance 11 horizontally. I split it twice, obtaining 3 logical qubits, and then I measure them.
Is there any way that you can see that from Entwine, or do you just know that?
You just need to know that. So the idea here is I just want to tease you a little bit and let you know that you may start thinking differently when it works with lattice surgery. All you need to know is that basically what you do here is kind of performing a joint ZZ measurements between them. So by doing this, you induce correlations, ZZ correlations on these two and on these two. And that's one way to basically do CNOTs in a more efficient way. You need to know that beforehand, of course. But yes, once you know it, then you can think about how to play with Entwine. I hope is that going forward. So I think Entwine, if you're Austin Fowler, you're beyond Entwine. Like you don't need this tooling, and you think already about it in a different way. But I think there is a very, very large set of the community that knows very little about quantum error correction or has partial information. And I really hope Loom Design, so Loom and Entwine, will help people onboarding into quantum error correction. Of course, we don't have enough documentation to make this process painless yet, but I hope that, maybe I do again a talk like this in half a year, in a year time, and we can see that the community, like we have more nodes and the community has grown and people are able to relate much more to these concepts. Again, go back to the IQM example. If they're gonna give us all these physical qubits and all these logical qubits, it'd be great if people know what to do with them. And I think this may start bridging a little bit the gap. And sorry for not quite answering straight to your question.
No, you answered. I guess I'm like I'm still, I'm a very beginner error correction
Mhm.
person, and I guess I'm struggling to see like what I could use Entwine for to like learn more about error correction.
Yes, I have a couple of examples at the end. Hopefully they'll do. Um, Let me get back to that. It's actually basically the next slide. So I just wanted to show you that I have this experiment, is the one we did before, exactly the same logic. I have my Entwine generated circuits. These are the splits here, isn't over 2 frames, but the same thing happens. And then I can use my steam converter. And again, I just look at my steam circuit and at the last three uh, elements of it. The logic is just slightly different for the two functions because we wrote the two notebooks at different times. But as you can see, the results are either all false or all true, which means that when I do my logical Z measurements, I projected either in the 0, 0, 0 or in the 1, 1, 1. So it worked somehow.
Sorry to interrupt, but
Yeah.
Nate, I think I thought of an intuitive way to explain the lattice surgery thing. If you imagine that you started with, so if you imagine each of the patches that you're seeing, each of the like little square quilts is its own qubit. If you imagine starting instead with three separate qubits, um, and then you're like, okay, I have these three qubits. Let me entangle them together. So in lattice surgery, doing an entangling operation is this grow operation. So it's kind of like imagine doing a C knot between them, rough, just really roughly. And then you've done that operation, and then splitting them again is like, okay, now I want to consider all of these three separate qubits again. Um, yeah, I don't know if that helps at all, but it's kind of like you have three qubits. I'm doing an operation which entangles them all together. That's when you have the one long qubit in the way that it's depicted here, and then you split them apart again. It's just in the example, you can't actually just start with one big qubit because yeah, logically you could do that.
Yeah. Okay. Yeah, that gives me something to go on. Thank you.
Yeah, I think that's on the right track. I mean, the way it's been explained to me when I when I became more familiar with lattice surgery is really all about performing joint XX or joint ZZ measurements and inducing correlations on the rest. A lot of what you're doing here when you measure these columns, it's basically kind of like a teleportation gadget, if you want. So if you think about teleportation, it works in a very similar way. You measure some of the stuff, and then you've teleported your qubit from the beginning to the second, or the first qubit to the second one. And here you're kind of doing something quite similar in some sense. Okay, let me wrap things up a little bit. So these are some of the codes we wrote internally. They're not part of the open source, but I just put them here to show that you can do more stuff. So you can do your rotated surface code, or you can do your BB codes, the things that IBM loves, or AGP codes. Again, you just need to create your syndrome extraction circuits, your stabilizer, and stack all of them together. Once you have them, then off you go. You can start building experiments and do everything you want to do with the simulations down the road. Now we had some kind of hackathon for Entwine. Oh, I think there is a slide missing. No, sorry, that's fine. So the question was something similar. So again, using Entwine as a designer tool. So the idea here was you want to find a sequence of lattice surgery so that you have a surface logic, like a surface code logical qubit, where each qubit of your logical are also logical qubits. You can think about a matryoshka kind of thing. So you want to generate a logical rotated surface code qubit, so something like this. But each one of your qubits, 1, 2, 3, 4, 5, 6, you want each one of these also to be a valid surface code qubit. So kind of a two-level encoding if you want. This is just a one way that somebody was thinking about drawing it. You can start seeing here like the XX and ZZ kind of measurements. And then they kind of, thought about a way of building it all. Now, this is not supposed to be an explanation of it, but basically you can figure out, you can make design choices by looking at this. And of course, it's not super easy if you're not familiar with lattice surgery. And I repeat once more, we don't have all the material to make people expert on it. But what I really hope we manage doing, and this is also part of my idea of sort of letting you guys at UF know about this, is it's a place where we could do it somehow. I think we have a lot to give. We're struggling to sort of put the code base out there and make it usable, but it will be great if we help the next generation of quantum error correction scientists to grow using these tools. And I think the visual part could be very useful for many of us. Just some summary, some conclusion, then leave some space for questions. There's going to be a video playing on the background just for fun. No, we need to start it. Okay, so today Entwine is a GUI online available. You can just use it however you wish. And Loom is open source and is a tool to build quantum error correction codes. So you can benchmark and compare codes. You can design codes from scratch. You can think about real-time decoders. That's something extremely interesting that I'm very passionate about. And I hope to see more and more of that going forward. And you can move out of sort of Steam-based simulations, so sort of just Clipper simulation, but going to something more. And the kind of general experiment that you see everybody performing will be the quantum memories. So quantum memories will basically just be you tweak your physical error rate and you see how your logical error rate changes. And the idea is that at some point you want to see a positive trade-off so that as your physical error rate increases, your logical qubit does not get worse, but it gets better. And finally, here is where the documentation is. So you have loom-docs, where there is the high-level tutorial and concepts, and then you have the API reference that contains a more thorough explanation of maybe why certain things have been done that way, what happens at the interpretation step, and maybe what happens first, what happens later, and why things were designed in that particular way. And with this, I conclude the presentation. I hope you had fun. You learned a couple of things about quantum error corrections. You're probably more confused than you were before about lattice surgeries, but such is life, I guess. Thank you.
Thanks so much, Leonardo. Any last questions anybody has for the speaker before we sign off?
I guess I don't know. I think always the best place to start with like learning or like using the tool to learn something is to like have an explicit thing you're trying to do. But I don't know. I guess like I'm curious, like can you use Loom or Entwine? Well, okay, first of all, I just want to say I love that you guys built a GUI. I think that's awesome. I want more GUIs in quantum, just for fun of playing with. Yeah, like are there maybe this is just like what's in the documentation, but are there specific examples you'd recommend of like just playing around with to learn more about, I don't know, both the stuff you've built, but also error correction in general?
Yeah, that's clear. Let me see if I have something I can.
And then just one follow-up after this is, do you guys do any decoding related work?
Yeah, good question. So I'll start with the decoding. We're not a decoding company, if anybody for Riverlane is here. So we're not active in the decoding space. What we want to do though, because it's needed, is we want to be able to deal with T-gates, those kind of simulations, that kind of design. So if you want to do those things, you need to be able to think about decoding, and you need to put the decoding part of the protocol into Loom, and that's something we are actively doing. But our idea is ideally is that the people will be able to do decoding, maybe using QRAC and penny lane, because you can join the two things, and so you can use the classical logic alongside the quantum part or the NVIDIA, and sort of trying to make decoding a bit demystified, if you want. Let me see if this one open source is too old. No, it's too old. Okay, I will show you one thing. It's not very simple to see. So we don't have enough documentation on Entwine, and we're also in the process of improving on that. But what you see here, and it won't be easy to see at first, but you need to have a little bit of trust on this. This is the skeleton for a 2-bit adder. So there is a bunch of tricks, but so like one of our chief product officer, which is one of our experts on quantum error correction, wanted to quickly have an example of exactly your question. How can I use Entwine for something practical? One interesting problem we're looking at is the adder. So you just take 2 bits and you add them together. And you can generalize this so that you can add any number. It's a non-trivial circuit. It requires T gates, and it's complicated to implement. So what you should think about is that on top here, there is really a T state factory. So something that generates magic states and put them down. And we don't have it here, right? And your inputs will be coming from here, and they're not attached to it. But this is the skeleton of how you can think about your algorithm unfolding. And it's all going to be about growing and shrinking and moving these patches through. Sadly, I don't have the circuit with me here, but basically what he did was writing out at first the sort of bare bones circuit, and thinking about ways in which you can optimize it, at least some of the obvious one, using ZX calculus and some other tricks. And then off he went and sort of just wrote the whole thing in Entwine, knowing a little bit what to do. So this is a clear example of something you can do with it. We had some examples from an intern. I wanted to ask him to put those online. It just hasn't had the time yet. For magic states, the distillation code, Reed-Muller distillation code. Again, something that involves 10 logical qubits and requires many steps can be nicely just put graphically down, and then you can start from there. Of course, the footprint for running these things is pretty high, and as soon as you have non-Clifford gates, how do you verify what you're doing is correct? It becomes complicated.
So once you built that thing, this is just a different representation of that object, right, that we were looking at?
Correct.
So once you built this, then you can take the code on the right and you can simulate it, right?
Yes. So in this case, you can simulate it. I mean, I don't know if there are measurements at the end. It's going to take a long time to generate because there's a lot of information. But yes, you can just execute it. Yeah.
Is there any way that you can then take it to hardware?
Good question. So yes and no. One crux of quantum error correction is if you need to wire your QEC code. So if you need routing, if the match between your logical qubits and the hardware is not perfect, it's going to be tough. If you're targeting a ion trap, something all-to-all, then that's relatively easy. So some memory experiments, or a bell pair preparation, or even trying something with T gates, if you take some shortcuts, that you could run on the larger devices from Quantinuum, for example. And you could try to run that out of the box. Of course, again, those devices tend to have different error correction codes. They do stuff differently because, ion traps work very differently to superconducting. But you can. So if the code you get in QASM or through GAPI or through CUDA-Q can be executed on a quantum computer. The performance will still be very poor, and you're unlikely to get active error correction just because no one really supports it. Yeah. But yes, you can, and ideally you would want to.
Okay, cool.
I can tell you this is again not part of the open source, but we had a project with quantum machines where we have generated the pulse sequence. So we're working at the pulse level, and there we were streaming the data out of the pulse control unit to the external decoder that was sitting on the sort of NVIDIA DGX cluster. So we did not use a GPU decoder. We just thought a simple decoder for testing purposes, but we were able to run the full quantum error correction loop, basically. It's an interesting time. The hardware, the classical hardware is almost ready to do it. The quantum hardware is missing, and you don't have any programming language that allows you to do that. So good luck doing this purely with Qiskit. Quantinuum has some really nice stuff out there. But there is an entry barrier, right? It's not super easy to use their stack. So again, I think trying to make all of this easier for people and onboarding both on the software side and on the theory side, I think will be very, very important.
Cool. I had a couple questions that came to mind. I think you mentioned you showed the TQEC visualization a couple of times, but I think you mentioned there's like some subtlety where it's not like directly integrated or something like that. Or did I miss something?
Yeah, so you just cannot program it using their stack. So we had some chats with Austin. Of course, he thinks Austin, for those who do not know, is one of the lead people behind that project. But he thinks that way of visualizing things makes way more sense, and I think he's correct on many levels. It's just maybe not so easy for people to get started with that one. So I think there is merit in having a simpler or more intuitive way of designing things. But again, we're talking with Austin, and we just want to make sure that because there are certain other things that our tool does a bit better. Not least, you can do more than just surface codes and lattice surgeries. So you can define any code you want as long as it's a stabilizer code. So there may be ways of integrating the two tools in a more profound way. At the moment, we just have a visualization that reflects what you've drawn on Entwine.
Gotcha. Okay. Yeah, that was what I was curious about. And the second one was about non-surface codes. I think you mentioned that on the like closed source side, you've got some of the BB codes, ones that have more non-trivial logical operations. So I was curious. I don't know how much you're able to share, but about any kind of hurdles that you have overcome or been kind of climbing over in defining logicals for other types of codes.
Yeah, so I mean, at the moment, we always work with codes that somebody already figured out how to deal with them. So it's more like reproducing what exists in the literature. The advantage is that once you've done that, then potentially you can share it very easily with people. The most difficult part is if you're an external contributor, you will need to figure out how we have thought about the data structure and whatnot. So it will take a bit of time to sort of convert ideas into Loom and Eka language. For our developers, it's just a bit painful sometimes because you still need to write eventually the circuits and whatnot, but it's doable. What I want to say here, and of course you're not recording, so I can freely say this, right? Ideally, someone goes and adds the BB code to the open source repository, and then at that stage, it's much easier internally to lower the pressure on that part of the code, and then also release a bit more maybe of some of our abstraction that we already have. It's a trade-off between what we think could be purely marketable and what is less so. So a lot of these things per se on their own should be open source. It's just always for a small startup more difficult to justify that choice. So getting some traction from the community will definitely make it easier for us to contribute with those slightly more exotic codes. But in general, it's very easy okay, it's relatively easy to add new codes to the code base. And indeed, it's something that at some point I will formalize a bit more and maybe see if there are some good ways to maybe use some of the micro grants to extend the code base in a bit more of a controlled way. Yeah, I answer at least half of your question.
Great. Yeah, thanks so much for your time. Really appreciate it. I think we're just about at time here, so yeah, really appreciate your sharing this with us, and we will definitely be sharing around the video. And if you'd like to share your slides in the just reply to the email invitation, that would be great, and we will definitely let the community know about the tool.
All right, perfect. Thank you very much.
Thank you, Leonardo.
Thank you.
Bye bye.
Take care. Bye. Bye bye.